Hello and welcome to video number 3 in the series of building a Class E transmitter. Now just to recap, Class E transmitters are solid state and they're high efficiency, can be made for high power, and they can be made at relatively low cost. So this series of videos is showing you how I'm building mine and putting my own twist on things. Now if you want detailed instructions on how to build one of these yourself, what you need to do is go to classeradio.org. It's not my website. It belongs to Steve WA1QIX in Massachusetts. And I have it up right here. That website will give you detailed schematics and instructions and anything you want to know about building these transmitters. So, in the last video, we demonstrated this silver box here. This is the phase splitter and duty cycle adjust board. And I told you back on that video that I was going to build a crystal oscillator as the signal source for this module. Now how this works, you put 12 volts in here, and out you get 2 square waves 180 degrees out of phase with an adjustable duty cycle at 1/2 of the crystal frequency. So let's take this over to the desk and I'll show you what we've got. So first I'll show you both square waves again so you can see where we stand with that. Now what I discovered was that when I was using this Chinese digital DDS-VFO, that when I was adjusting the duty cycle on this board, sometimes it got a little squirrely, and the waveforms would just get all distorted, and it was really tricky to get it tuned in properly. Well, after I built my own crystal oscillator, man, it worked beautifully, and I'll show you what I think it is. I think what the problem is that the DDS-VFO may have a slightly dirty output. Can't see there. So on my crystal oscillator, on the output, I built I put a pi filter, a low-pass pi filter, to make sure there were no harmonics in the signal. And it's clean going into the board, and I think that probably did it. Now when I built this, it has a crystal oscillator with a buffer, but the output was too low to drive the board. So I thought, well, I'll add another buffer, I'll add another stage to increase the output. So I did that. I put a second buffer stage on there, and the output did get larger, but it still wasn't enough to drive the board. And the problem arises on the JK flip-flop. On the clock input, I have a 100 ohm resistor going to ground, and that tends to drag down the signal. So it just wasn't enough to drive it. So what I did was borrow one of Steve's ideas, went to his schematic, and I put another stage in the box here, and I capacitively coupled it, and the emitter on that NPN transistor goes through that 100 ohm resistor, and it just, I turned it on and it worked first time, didn't even need to adjust it, so it works. So let's turn this on. All right. And here you can look on the scope. Now, these are the 2 square waves, and now I'm going to adjust these. I'm going to adjust one of the waveforms. We'll see which one I'm adjusting here. If you can look at the scope, yeah, there you go. So if you look, square fell off here. So if you look at the yellow one closely, you're going to see right now it's narrow and it's going to get wider. See how it's getting wider? It's adjusting the duty cycle. And the blue wave, the second phase, works correspondingly the same way. So let's show you the input coming into this thing. I'll take away one of the outputs here. This is the trigger one. I'll leave that one on. So I'll go on the other side of the pie filter. And if you look, this is coming out of the crystal oscillator board. So if you look at, it's a nice clean sine wave at 7740 kilohertz, which is twice this frequency of 3.870, our operating frequency, megahertz. So that's the output coming off of the, coming out of the board, the crystal oscillator board. And now I'll show you the input going to the clock. There's the clock input. So how the JK flip-flop triggers is on the negative going pulse on the sine wave. Even though that isn't a perfect sine wave, it's just used as a trigger. So it doesn't have to be a perfect sine wave. And it triggers every time it goes down, so therefore you get half the frequency. So that part is all done. Now, in the next video, I'm going to build the MOSFET drain power supply, which is the 22 and 44 volt DC high current power supply, and the analog Heising modulator. Now what that does is that takes, when you talk into the microphone, through the microphone preamp and through the audio amplifier, public address amplifier, couple that into this Heising circuit. That's what gives you the voice modulation on the transmitter. And I'm going to do that using basically, these are the main components. This is the power supply transformer, capacitors for the filtering of the DC, and this choke and this capacitor will be the main components of the modulation Heising circuit. One of the nice little bling I picked up for this, I was at the metal store the other day, and I found these steel boxes that are the perfect diameter hole, that have the perfect diameter hole for these meters that I'll use for metering. So this first hole will be drain bus voltage, MOSFET drain voltage, and these two will be the drain currents phase 1 and phase 2. The power supply will be in this bottom rack here with this old antique meter, and the Heising modulator will be in this next rack up. So there we are for video number 3. If you want to see these videos and more of my other projects, you can go to mycaliforniaradio.com. Thank you very much, and see you next time.